Imagine a long list of Saturday errands. You must hit the grocery store, the hardware store, the pharmacy, and the post office before dinner. Figuring out the absolute shortest path to visit all those stops is a classic math puzzle known as the traveling salesman problem. If you plug those addresses into your phone, your mapping software solves that puzzle in milliseconds. It instantly draws the most efficient connecting lines, telling you exactly how many miles to drive. We solved this routing problem on Earth because our destination cities and storefronts are permanently bolted to the ground. They stay perfectly still, waiting for you to arrive. But the math breaks if you try to plan those errands to visit 10 different asteroids scattered across the solar system. We are dealing with massive, irregular rocks drifting through the total isolation of deep space. Unlike a grocery store, an asteroid never sits still. Each one is screaming through the void at tens of thousands of miles an hour. This creates a problem called space-time dependency. If your spacecraft departs even 1 hour late, your target will have moved thousands of miles. Your original path will lead to empty space, forcing you to take a much longer, sweeping curve to catch up. This is the asteroid routing problem. It's a mathematical challenge where drawing straight lines is impossible, and every tiny delay means recalculating complex orbital curves and speed changes from scratch. Calculating every possible curved path to a group of moving targets would take supercomputers years. Because the math is so heavy, engineers usually have to settle for highly educated guesses to plan their routes. However, when you're dealing with billion-dollar space missions, a guess isn't enough. Scientists need a path that is mathematically perfect. To find it, researchers built a new framework. They started with a decision diagram, which creates a layered map of hundreds of potential multi-stop routes. To make this map work without crashing the computer, they used a shortcut. They told the simulation to pretend that waiting in orbit before departing for the next stop costs 0 time. By removing that one time constraint, the computer can rapidly sketch out a baseline map of promising paths without getting bogged down by the physics yet. Once that rough sketch is ready, a specialized algorithm called peel and bound takes over to turn the sketch into exact science. The algorithm takes one single, complete route from the sketch and runs the full physics math on it. This establishes a gold standard score for the entire mission. Then, the algorithm starts calculating an alternate route. As it draws this new path, it constantly compares the rising cost of time and fuel against that golden baseline. The exact millisecond a new route's cost exceeds the baseline, the algorithm stops. It throws that path away and stops wasting processing power on it. If a different route actually requires less fuel and beats the score, it becomes the new gold standard for the computer to try and beat. By combining a rough sketch with this ruthless pruning, the computer only focuses on improvements. Eventually, it reveals the one path that is mathematically perfect. When the researchers tested this framework, the algorithm calculated the perfect trajectory for 10 moving asteroids in under 2 hours. When they tried even bigger missions, visiting 15 to 30 asteroids, the algorithm found the best solutions faster than any method used before. These calculations will be necessary as we begin mining resources from distant rocks, or launching probes to study the earliest days of our solar system. Wasting rocket fuel on an inefficient path can make a mission impossible. Finding the optimal route allows us to explore further while spending less. There is still one catch. The simulation currently assumes a spacecraft can change its speed instantly, like a sudden, powerful burst from a rocket. In reality, future missions will likely use ion drives, which provide a low, steady push over long periods of time to build up speed. But even with those adjustments left to make, starting a mission plan with a proven baseline is a massive upgrade over relying on guesses. It is only a matter of time before this math is used to plan an actual multi-stop mission into the asteroid belt. The universe is a chaotic dance of constantly moving targets. We finally possess the cosmic GPS required to navigate it.